In today's video, what we are going to talk about is momentum, and impulse. Momentum and impulse. Now, when you think of the word momentum, I'm sure there's a lot of things that come to mind. Momentum is a pretty common word and is used in a lot of things. For example, like if you're watching a football game or something like that and you see a really big player moving or running, you might think, wow, they've got a lot of momentum, right? So typically when we see things that are really big, like a big truck or something that's moving like a semi or a train that's moving really fast, you can say that that thing is moving with a lot of momentum to it. And that would be correct because momentum, when we're talking about momentum, momentum is, and in fact, we're going to write out the equation for it, momentum, which we use the symbol P for momentum. Don't ask me why. I'm sure there's a good reason for it. I actually just don't know the reason. But we use the symbol P for momentum, and momentum is equal to the mass times the velocity of the object. So when we're thinking about the momentum that something has, we take into account how big that object is and how fast it's moving. So let's say the mass of it stays constant. The slower that it's moving, the less momentum it has. But the faster it's moving, the more momentum it has. It would be like, let's say I were to throw a baseball at you as hard as I can. If I were to throw a baseball at you with my science teacher arms, it's probably not going to have that much momentum and it's probably not going to hurt you that much. But if we take a Major League Baseball pitcher and he throws it with a much higher velocity, right? The mass in each case is the same, but if we just change that velocity that that baseball is traveling with and that Major League pitcher throws that baseball at you, you're going to feel a little more momentum from that baseball than, let's say, from me throwing that ball. So there's our equation for momentum. It's just simply taking the mass of the object, multiplying it by the velocity, and that's the momentum. So let's write down a few things about this. Momentum is the product of an object's mass and velocity. Simple as that. Now, if you have something that is traveling at a constant velocity, and we're going to assume that if we're dealing with just a singular object, the mass most likely isn't changing. So if the mass is staying constant and the velocity is, if it's moving at a constant speed or a constant velocity, that means the momentum is staying the same. So we'll say if mass and velocity are constant, then momentum is constant. Doesn't change. Momentum is constant. Now, we obviously can change the momentum of objects. So let's say we go back to that baseball example. If I throw that baseball as hard as I can at you, it'll have some momentum, and the velocity will be slightly changing a little bit. So maybe the momentum will be changing just a little bit. But let's say in a perfect world, let's say I can throw that baseball with a constant velocity at you, and as it's traveling at you at a constant velocity, it's got some momentum, and it's going to change its momentum once it hits you or you catch the ball, right? Because its velocity is going to change. It's going to go from whatever velocity it had and it's going to go down to zero velocity. And so therefore at that moment of you catching the baseball, you're changing its momentum from that contact, from that force of your hand on the ball, you're going to be changing the momentum. And the reason able to change the momentum is because there's a net force. In other words, your hand acting on the ball. And so what we see is that the only way that we can change momentum is if there's a net force acting on the object. If there's no net force on it, according to Newton's laws, it's just going to continue at a constant velocity. And so therefore, whatever momentum it has will just stay the same. But if I can get a net force acting on the object, then I can change the momentum. So we're going to say that momentum will change if there is a net force acting on the object. On the object, which brings us to impulse. So impulse has to do with that change in momentum. So over here, impulse is a change in momentum. So in the example of the baseball, you are providing the impulse. Your hand, the force of your hand is the impulse acting on the ball, which causes it to change. It causes its change in momentum. So impulse is a change in momentum. Another way to phrase this, we're going to say, is it's a certain amount of force. So there has to be a force involved for this. So a certain amount of force. Because remember, we have to have a force. If there's no force, if there's no net force involved, you're not going to have a change in momentum, so you're not going to have an impulse. So a certain amount of force over a period of time. So we have to have time in this. It's a certain amount of force for a certain amount of time. And time has something to do with it because think about it like this. Let's say we have a truck, okay, and this truck, here's our truck, it's traveling along the road. Let's say it's traveling along the road at like 50 miles per hour. Okay, here's our truck traveling along at 50 miles per hour. It's got some momentum to it because it has a velocity and it has a mass. We won't worry about the mass at this point. But it's traveling along, and then all of a sudden, out of nowhere, just popping up from the ground, out of nowhere, we get this brick wall. Brick wall pops up out of the ground, and the truck runs right into this brick wall. And we know that if this truck runs into this brick wall, well, it's going to kind of crumple up and it's going to come to a very abrupt, here's my crashed truck here. It's going to come to a very abrupt stop and it's going to go down to 0 miles per hour. And it's going to happen in some amount of time, a pretty short period of time it's going to take for it to go from 50 miles per hour to 0 miles per hour. It's not going to take very long if it's running into this brick wall to do that. So its momentum changes over a very short period of time. Large amount of force from that brick wall over a short period of time. Let's say I take that same truck, and this time, let's pretend that that is the exact same truck. This same truck, and this time, to get it to slow down to 0 miles per hour, this time what we do is we have a ginormous pile of Jello. A ginormous pile of Jello just pops up from the ground, and this truck, still going 50 miles per hour, runs into this pile of Jello. And if it does that, it's not going to come to an abrupt stop like it did up here. In fact, it's going to probably continue for a little while through this Jello. It might even go all the way through, but let's say this is some pretty thick Jello, we'll say. And so it doesn't go all the way through, but it goes most of the way through. So the truck kind of goes most of the way through and finally comes to a stop eventually, right? And so in each case, we see that the momentum, the impulse, is actually the same. The impulse that the truck has here is the same because it's going from 50 miles per hour to 0 miles per hour. So the velocity is changing from 50 to 0. And here we're going from 50 to 0 miles per hour again. So the impulse is the same. But in this case, it took the large amount of force over like just a few milliseconds, whereas this, very small amount of force, but a longer period of time, right? So as we're going to see, those two variables can change, but the impulse is actually going to be the same on both of those. So impulse, we have to look at not only the force that's involved, but also the amount of time that is happening during that impulse. So impulse is equal to the force, the net force, times the change in time. So again, the impulse is the same for each of these examples. It's just that this has a very large force, small amount of time, large amount of time, small force from the jello. But the impulse, or that change in momentum, is the same. Now watch this. Ready for some really impressive math? Here we go. We're going to relate the impulse with the momentum through some pretty crazy math. Ready? Here, get ready. We're going to take Newton's second law. Force is equal to mass times acceleration. All right? Now here's what we're going to do. We're going to change this acceleration term right here to change in velocity over time, because that's what acceleration is, right? Acceleration is the change in velocity over time. So we're going to go force is equal to mass times the change in velocity over the change in time. Okay? So all we did was just change what the acceleration factor looks like there, the acceleration term looks like. Okay, now what I'm going to do is I'm going to multiply each side by the change in time, because I want to get mass and velocity by itself, and I want to put force and change in time together, because hint, hint, if we look here, impulse is force times the change in time. So I'm going to bring that change in time over here. So it's going to be force times the change in time is equal to mass times the change in velocity. And hey, look at this. Mass times velocity, force times the amount of time. And look at that. I've got impulse and momentum. See that? And so what we can actually do is we can replace this over here. We can get this. So the impulse, force times the change in time, is equal to the change in momentum. Right there. Impulse is equal to the change in momentum. This is called the impulse momentum theorem. Oops, impulse momentum theorem. So basically it's relating our change in momentum and the impulse, or the force essentially, that an object feels to change its momentum. And so in the next video, what we're going to do is we're going to take these equations here, we're going to see how we can solve some different problems, problems like this. We can figure out different variables based on that.